Okay, continuing from where we left off the previous section, this is part 2 of CTFT, is that Fourier series is applicable to continuous periodic signals and has a discrete single-sided spectrum with infinite number of harmonics. The continuous periodic complex version has discrete but two-sided spectrum, which comes about from the fact that the harmonic indexes by which we multiply the fundamental frequency span both sides of the origin. But what do we do if the signal is not periodic? And as I discussed at the end of the last video, if we have something like this, which is not really a periodic signal, can we do a Fourier analysis on this? Well, this is another term used for aperiodic signals, and that is Fourier transform. So we said that the way we think about the problem of this nature is that when you have a periodic signal, something repeats with a certain period. And it could be anything. Let's say in this case I said that the period is 5. But if you change the period to 10, you can still do Fourier series analysis on this. You can change it to 20, you can still do it. You can change it to 100, you can still do the analysis. But what if you make this infinity, super big? Now this signal appears to be aperiodic. It's no longer repeating because the period is so big that the signal might as well just be by itself. In such a case, the fundamental frequency, which is a finite number, becomes so small that the resolution becomes continuous. And if we had a spectrum of this nature before, and as we increase the periods, as you can see, these little little impulses come closer and closer together, that ultimately the frequency resolution becomes continuous. So CTFT has a spectrum that is continuous. Now I'm going to shift into the development of the CTFT equations. Fourier series is written like this. This is the time domain equation, and the Fourier series coefficients are developed like this. Fourier transform, on the other hand, is written in this fashion, where this big X omega is the Fourier transform, and then the expression for that is this. Whereas the period here is T0, here is infinity. So now let's shift into how this expression is actually developed from Fourier series to Fourier transform. And it's not very often shown in books, etc. So I'm not sure if it's covered in your classes or your books, but here it is. Okay, now we're going to look at how to develop the CTFT expression. And we call it expression because that's what it is. It's some clever manipulation that we're going to do the Fourier series equation so that it will apply to a case where the period is not finite and in fact infinite. So let's start first with the equation for the Fourier series coefficients, and that is written as CK, where K is the kth harmonic, C is a number, a complex number, but it is just a number, and it's 1 over T0, which is the period. We integrate over half the period from negative to positive. Then we write x of t. Then we write the complex exponential, which is j k omega 0 t dt. So this is the FSC equation. Let's call it 1. To apply this to an aperiodic case, what we recognize is that we have to allow T0 to get fairly large, this number right here. In fact, we allow this to go to infinity. But as the period gets longer, we're faced by division by infinity. And we don't like that. So what we can do is we can express this period in form of frequency, which will take it from denominator to numerator. But we still have a little problem because we have the issue of multiplication by 0. Anyway, well, let's start. So let me change the color back to 0. Okay, now frequency is, as we know, is 1 over t, and frequency in radians is omega over 2 pi. And let's stick a 0 in here to make it all consistent. As t0 goes to infinity, what we have is something like this. Limit t0 goes to infinity of 1 over t0, this term. We can write this in infinitesimals as delta w over delta omega over 2 pi. I tend to call that w because it looks like w. We can rewrite the FSC equation, this one, using this expression in right here. So let me rewrite this equation again in black. CK is equal to delta omega divided by 2 pi, but now the integration will take place over the infinitely long period, x of t e to the minus j k omega 0 t dt. Once again, delta omega is now approaching 0, so that's not so great either. So this is not so great. Okay. So to get around this issue, this is not panning out for us, so let's do this. Let's go back to the time domain equation, Fourier series equation, which is written as x of t equal to summation, because period is finite, k from minus infinity to plus infinity, ck, same ck, e to the positive exponential omega 0 t, and no dt, etc., because this is summation. This is FS Fourier series equation number 2. This is the time domain. This is the synthesis, and that's the inverse. Now, what we will do is we are going to do something interesting. And now we're going to, let me get my color pen again. Okay, this one, I picked pink. Okay, then I'm going to take this expression right here, and I'm going to put it right there. And I can rewrite this equation like this. X over t, x of t, time domain signal. Again, k goes from minus infinity to plus infinity. Now I'm going to plug this whole thing for that, and I write delta omega over 2 pi minus infinity to plus infinity, x of t, e of minus j, k omega 0 t dt, and then this term goes here, j k omega 0 t. So there. And all I've done is I have taken this expression, the not so great expression of ck, and plugged it into the time domain equation. So this right here is our CK. Now what we're going to do is we are going to change delta W to delta, I called it W again, delta omega to d omega. And k omega 0 to just omega, because the frequency is now continuous, and the summation in this equation will now become an integral. And we'll move the 2 pi factor to the front, and we rewrite this equation as x of t equal to, we're going to move the 2 pi factor to the front, I made a little error here. I need the integral from minus infinity to plus infinity, and then I'm going to put this expression in here. Minus infinity to plus infinity, x of t e to the minus j, after making this substitution, j omega t dt. Same here, this becomes omega, so e to the j omega t, and d omega, which actually comes from here. So I move that here. Now, again, let's go to this one. This part of the equation is CK, and in fact, equivalent to CTFT. It's called, it has a special name, CTFT, so we'll rewrite this as, let's go back to this one. I'm going to write this, oops, I picked the too fat. I have to delete it. Okay. Big X. I'm going to call it big X. Big X as a function of omega. So big X is equal to minus infinity to plus infinity x of t e to the minus j omega t dt. You see, that's all I've done. And this is CTFT. And x of t, then, if you just write this term over there, is 1 over 2 pi. Integral again from minus infinity to plus infinity. X of omega, that's this guy right here, e to the minus j omega t dt. So this is the I, or the inverse CTFT. So here we have developed the equations for a continuous time Fourier transform from Fourier series equation. If it's not clear, perhaps you will rewind it and watch that again. Now I'm going to shift over to looking at some properties of CTFT and how they relate to some important functions. But one other thing I wanted to show you is that typically the way it's written is if you have a time domain, let's go, time domain function x of t, and we want to write a CTFT, we write it like this, CTFT. We just make a big and then this function of omega. And if you have y of t, and we write then big Y. And in fact, sometimes it's also written this way, x of t. There's a fancy Fourier transform, x omega. Sometimes it's shown in this fashion. And both of these are actually bidirectional because the process is considered linear. So now let's go back and look at some properties of CTFT.